Hey you guys, here is one of our first videos here about chapter one, starting our class with studying chemistry. Chemistry is the study of change. So this is chapter one, and we'll start to look at what does chemistry mean. And I'm sure you guys have taken chemistry before, or at least heard about it since you were little, and you would talk about atoms and protons and neutrons and electrons, and we'll be doing the same thing here, but hopefully a little bit more depth. So as far as chemistry, this little hieroglyphic, it's not a hieroglyphic, it's like a Chinese character that means change. And that's what their word for chemistry is change. So chemistry is the study of matter, of course. So basically it's the study of everything and the changes that it undergoes, often called the central science. And, it's like you need chemistry for everything. You don't necessarily need biology for everything, but you need chemistry for everything because it is the study of everything, because it's the study of matter. So you'll probably be required to take chemistry, really almost no matter what field you're in, even psychology, I think they have to take chemistry. So, well, I would say so, considering they're studying the brain and the chemicals of the brain. So basically, it makes sense that chemistry is in everything. So you see sanitation. If we didn't have chemistry, there would be a lot of human feces everywhere. Actually, there wouldn't. It would just be in piles. But at the same time, the bugs probably couldn't keep up with it. So what we do is we treat it with chemicals, and we treat it in such a way as to isolate solids and liquids, and then treat it in different ways. So without chemistry, sanitation would be not as sanitized, if you will. All these different areas of chemistry are involved as far as anesthesia, vaccines, antibiotics. Of course, you'll see um, uh, biology in here, gene therapy, of course, understanding the genetic code. Those are chemicals. That's nucleic acids. As far as energy in the environment, of course, fossil fuels are as a chemical that undergoes combustion, which then produces certain products. So these are all chemistry related. And nuclear energy is nuclear chemistry, where you're studying the chemistry of the nucleus of the atom and how it undergoes changes. Materials and technology, all these different materials are, you need chemistry to understand. Polymers and ceramics, all these different materials that do different things for us are come from chemistry. Molecular computing is a pretty neat field in which they're using molecules to do things as far as molecular switches and stuff like that. That's pretty fun. Food and agriculture, of course, if we didn't have GMOs, even though I know that that is kind of a bad word nowadays, those genetically modified organisms or crops help us to have larger yields. Pesticides, of course, and herbicides have helped us to have larger yields in food and agriculture, but you could also argue it's destroyed a lot of the planet. But hopefully chemists are learning from their mistakes and coming back with other chemicals or other more natural pesticides and herbicides that will help us to have a higher yield. Now, how do we think like a chemist? The fun part of understanding chemistry, I think, is understanding what's going on in things that you can't see. So in this picture here, I have a picture of a dissolving sugar cube. So this you could just label as sugar. Now this would be, of course, we're in chemistry, so we're going to label it as a solid. And it looks like it's dissolving. So what's happening here, these are called dissolving lines, and these dissolving lines are actually a different density of the surrounding solution, and that's why they reflect light differently. Now, if you were showing this as a chemical reaction type of thing, you might write the word sugar here, and then you might put AQ or aqueous with it, because now it's sugar, but it's still sugar, but now it's in the aqueous solution, if this, of course, is water out here. So I think that was a pretty neat picture that is in your book, I believe. Now, what I have here, I don't know if I can show this. I might have to show you during the WebEx. This is a video, and this video is showing a simulation of these are sugar molecules and them dissolving. So I don't think it's going to work here. I'm going to have to show it to you on the WebEx. So how do you think like a chemist? You see an anthill and you think ants. You see a sugar go away and a cube go away and you think, where did it go? It went molecularly into the solution down here. So thinking like a chemist is thinking on the molecular level. Oh, there it goes. So you can see that what's happening is the sugar molecule is being drug away by the water molecules. And the reason that's occurring is because of the interaction between hydrogen bonding between oxygens, which are red, and hydrogens, which are blue. Hydrogens are actually white, but what they're showing there is that there's an attraction, and there was an attraction between the water and the sugar, parts of the sugar molecule. So this is a covalent compound, sugar is, so you didn't see it break apart, you just saw it stay an entire molecule of sugar. So over here, you'll notice that sugar stayed sugar, but now it has an aqueous label. It didn't turn into ions, whereas ionic compounds that dissolve turn into ions. So thinking like a chemist is envisioning it in this fashion. So again, here's something thinking like a chemist. Here you see rusting, but you don't see, you think, well, what is rusting? And you ask yourself those questions. What are the materials made of? Macroscopically, you see the rust, but microscopically, you know that the iron is undergoing a reaction, chemical reaction, with the oxygen to make iron 3 oxide, also known as rust. So this is a chemical change, and a chemical change is where it changes into new things. So when we think like a chemist, we want to be able to write everything in symbols, and those symbols indicate a few things. They indicate who it is, and they indicate its oxidation number. Oxidation number of iron in iron metal is 0, and then because it hasn't gained or lost electrons at this point, and then it reacts with O2. Now, so that's elemental, that's a gas. And when they're an element, has not gained or lost electrons, and then it made Fe2O3. Now, Fe2O3 is one of the forms of rust, the end of the line form of rust. And if we balance this, it looks like I'm going to need to put a 3 here, and then a 2 here, and then a 4 here. So that's a balanced chemical equation, and that's showing that 4 irons and 3 O2 molecules combine to react and make iron 3 oxide. So that's the microscopic or even submicroscopic. You can't really see this with a microscope. You'd have to have an electron scanning electron microscope. So going on with thinking about chemistry and the scientific method, you've probably heard about the scientific method often in your life, but the scientific method is a systematic approach to research. Usually there's some sort of observation, then a hypothesis is put forward, which is a tentative explanation, and then you can test and modify this hypothesis over and over again in this little circular fashion. A hypothesis can then go on to be, after much testing, and go to a theory and then to a law. It can tell us information about the universe, that it acts the same in all those same conditions. It's a law. So like force equals mass times acceleration is always true. It's a law. A theory explains a body of facts and tells us how and why something happens. A law tells us what is happening. That's the difference between these two things. A law versus a theory. A law tells us what. A theory says how and why. So the atomic theory is saying how and why atoms are arranged and why they undergo reactions the way they do. So atomic theory explains matter in the form of atoms, which are teeny, teeny, tiny pieces of that matter. So what is chemistry? It's the study of matter and the changes it undergoes, like we already said. Now I have a video I want to show you here. I think I'll show you that on the WebEx. But either way, it shows how something is chemically changing. So matter is anything that occupies space and has mass. Now here's some definitions. That's what we're doing here. A substance is a form of matter that has definite composition and distinct properties. Very general terminology. So all of these things that you see in the picture here is matter. Liquid nitrogen is matter. N2 gas. Gold ingots is matter, and that would be AU solid. Trying to draw a little S there, and these zeros would mean it's not undergone chemical combination. And then this is silicon crystals, and silicon, I don't remember how silicon travels. I think it travels individually. I'm not sure. Sometimes things travels in fours, like phosphorus travels in fours. But either way, it's a solid. It's a metalloid. So this is all matter, and these are all substances. So a mixture then is a combination of 2 or more substances that retain their distinct identities. So homogeneous mixture is a composition of the mixture that's the same throughout, like soft drink, milk, or solder. Solder is where you solder things together. It's actually a homogeneous mixture of lead and tin, I believe. Lead and tin, so it's like an alloy, a very low melting point. And then you can use that melting point, low melting point, to melt it and melt things together like circuits. But these are all homogeneous. Milk is homogeneous throughout. Heterogeneous is not uniform throughout, like the cement or iron filings in sand. You can see the different parts of it. So that's a heterogeneous mixture. Physical, now a physical characteristic or physical means can be used to separate a mixture into its pure components. So physical means we're talking about being able to separate a mixture. Now this mixture cannot be chemically combined then, and that's the point. The things in the mixture are retaining their own individual identities. So physical means can then be used to separate them, like a magnet or distillation. So here's a magnet separating the iron from the sand, and here's distillation, that is distilling different types of liquids away from each other. But the two different types of liquids were never chemically combined down here. They were the same liquid. They were their individual identities. Now they just get separated through distillation. So a physical means can be used to separate a mixture as long as they're not chemically combined, because if they were chemically combined, they would not be a mixture. So let's talk about what an element is. It's a substance that cannot be separated into simpler substances by chemical means. Cannot be separated into simpler substances. So if you have a compound that could be separated into its elements, like H2O can be separated into hydrogen, of course, and oxygen. But then hydrogen and oxygen are elemental. So 114 elements have been identified. I think there's more than that at this point. 82 of them occur naturally, like things like gold, aluminum, lead, and so on. These occur naturally, but they occur usually in some sort of combination. Aluminum, you don't find elemental in nature. You find gold. But aluminum, lead, all these things are in chemical combinations. Sometimes you can find mines of sulfur, though, which is pure sulfur, like this picture is showing you. 32 elements have been created by scientists. So there's usually in some sort of collider where subatomic particles are smashed together, or two medium-sized elements, and then larger elements are created. Here's some common elements and their symbols. So you want to know elements and symbols. So how many should you know? That's a good question. Generally, I always tell people to know elements 1 through 82. Now, that is a lot for sure. But sometimes you just have to memorize some things to really speak the language. There are some things above number 82 that are pretty common, like uranium. Uranium is a common element that you probably would see. And you'll see ones above 82 also. So just kind of have the periodic table next to you all the time. And I don't expect you to memorize the periodic table, but I do expect you to kind of know that O stands for oxygen, AU stands for gold. So 1 through 82 for sure, to know the symbol and their name. But what is a compound? Now, a compound is something that's when elements chemically combine in a fixed proportion. So all of these are compounds. Lithium fluoride is LiF. That's the chemical formula for lithium fluoride. Quartz is SiO2. And that's an actual polymer of many of them. And then dry ice is carbon dioxide. So these are all compounds in which are more than one element combined in a fixed proportion. And they can only be separated by chemical means. That means you would have to separate lithium from fluoride, you'd have to do something to it to chemically alter it. Because when lithium fluoride, to get into its elements, electrolysis you could use for this or something like that, where you apply some sort of energy to it and you can separate the elements. And F2 fluorine is one of the ones that travels diatomically. So we would need to have it like that. And then if we balanced it, look like that. I didn't put any phase labels on anything, but either way, that's a chemical reaction. Now, we just want to touch on the 3 states of matter, solid, liquid, and gas. Now, what's important in chemistry is the fact that it's a solid label, a liquid label, or a gaseous label. And so this is just your book had this picture of showing here's a chunk of ice and you see gaseous water or water vapor, and then solid water, and you can see its structure in here is kind of neat. That's why ice has a lower density than liquid water. And then liquid water would have a liquid label, and it has a certain type of arrangement of its molecules. Liquids are usually free-flowing. Solids are not free-flowing. It's like a chunk. They hold their shape. And a gas would fill the entire container, whether that was a room or just a small beaker. But because they are moving very fast, they're very hot. That's why they're a gas, and they would occupy the whole container. Now, different types of changes that occur, like a physical change does not alter the composition or identity of a substance, like melting or dissolving. Dissolving is a physical change. So when something dissolves in water, it has an AQ label. When something melts, it goes from a solid label to a liquid label. A chemical change, however, does alter the composition. So when you see something happening like hydrogen burning in air to form water, that is a chemical reaction, O2 plus H2 to make H2O. And this is like a little representation of it, showing it in molecule form. These are molecules. The word molecule is used for covalent compounds. So this is a molecule, 2 molecules of hydrogen, 1 molecule of oxygen will make 2 molecules of water. And I want to show you this video probably on WebEx, and that's where it shows the changes of chemical changes when sodium and chlorine react. What this is showing here is the burning of hydrogen. So hydrogen must have been created down in this tube, and then it was lit on fire, and as it was being created, it's burning with the oxygen in the air. So that's a chemical change. Now, as far as extensive and intensive properties, this is a terminology used for certain properties of matter that depends upon how much matter is being considered. An extensive property does depend upon how much, like mass, length, they depend upon how much, and volume. An intensive property does not depend upon how much matter, like density, temperature, and color. It's an inherent property of something. Like I can have a big chunk of something or a small chunk of something. If it's the same chunk, it's the same thing, it'll have the same density. Same with temperature and color. Now, this is where you might want to go do fun sheets number 1 through 5. We've covered that material. So the goal here is to watch these videos and then start working on those fun sheets. And then during our WebExing time, we can address some questions on those fun sheets. But let's continue on. Again, matter is anything that has mass and occupies space. I feel like I'm beating that to death, but I must have a reason. And that's because we're going into measurement. Measure is when you measure mass, you're actually measuring the quantity of matter. Now, the quantity of matter is something that has mass and occupies space. And it doesn't really matter where that matter is, whether it's on the moon or on the Earth. If it's on the moon and the Earth, it's going to have the same amount of matter. So it's going to have the same mass, but it might weigh differently because weight is dependent upon gravitational pull. So weight is the force that gravity exerts on an object. Now, since we never leave the planet, we might use those terms interchangeably, but something on the moon would weigh less, but would have the same mass. So 1 kilogram bar will mass at 1 kilogram on the Earth and 1 kilogram on the moon, which is what I was just saying. Now, as far as the SI units that we use to measure things, to measure mass is the kilogram. These are just SI units, which means standard international units. And that just means that if I say, hey, I'm measuring this in SI units, you know what I'm talking about. So that's really all there is to it. You can measure lots of length in different units, but the SI unit is the meter. So you just want to be familiar what these units are. So when I say put them in SI units, you know what those units are. Time would be seconds, electrical current amps, and so on. Well, I just whizzed by one of the slides that I wanted to show you. I do have something in D2L for you, and it's called SI units and conversion factors to print. And I want you to print that. Oh, you don't have to, but you can use that on exams and so on. And on the previous slide, there was the The conversion factors, the metric unit conversion factor. So when you get a chance, go to D2L and look up the SI units and conversion factors to print. It's in the syllabus module. And then half of it looks like this. It gives you all of these different formulas to interconvert various length units or mass or volume. It gives you some conversion factors for any of these, like imperial units, inches and yards, to the metric system. And it also gives you some meanings for units of energy, and also some formulas. Like here in chapter 6, we use these Q equals ms delta T equation, where Q means heat. And that's something else that's on this sheet of paper for you to use during exams. And here's a constant that's called the ideal gas constant, and we'll use that in chapter 5. So all these different pressure units have conversion factors, and then our temperature has conversion factors, and then the SI unit is given in each one of them below that in the gray area. So let's keep on talking about measurement. We can measure volume. The SI derived unit for volume is a cubic meter. Now, a cubic meter is monstrously huge, and that's why we don't really use that too often, but it's the SI unit. What we do use is a decimeter cubed, which is actually a liter. So we will see that a little bit more often because we use milliliters and liters in our lab work. And we also, I want you to notice that 1 centimeter cubed is equal to 1 milliliter. So when we use density, we'll be interconverting between those, and there it is down here again. So if I have a density for water of 1 gram per milliliter, that's the same thing as a density of 1 gram per centimeter cubed. So volume, a lot of times we'll use volumetric flasks, and volumetric flasks only measure 1 volume. This is a 1 liter volumetric flask. So when you guys do your glassware scavenger hunt, you're going to see some things like, oh, how do I measure using a volumetric flask? If I were to take a reading for this guy, it would be 1.00 liters. Volumetric flasks usually almost always read to the hundredths place. And so even though it just says 1 here, if you were to use this in an experiment, you would record 3 significant figures to it. And this would be your estimated digit. And these are your certain digits here. So anyway, it's just a little aside because volumetric flasks people are not as familiar with, so they think, oh, it's just 1 liter. But it only measures 1 volume, and so you read it to the meniscus, and it's 1.00 liters. And there's that thing again. You don't want to forget that because that's pretty common to use to interconvert those two. So let's talk about density. Density is in grams per centimeter cubed, and it's the amount of matter in a certain size of a sample. So it's a reflective of how tightly packed the substance is. So you can have a chunk of gold, and if this was a chunk of gold and you had the same size chunk of aluminum, for example, the same size chunk of aluminum would weigh a lot less. Its mass would be a lot less, because of the fact that aluminum is not as tightly packed. So if you could zoom in on here, the atoms of aluminum would be further apart than they would be in gold. So density is reflective of the packing of the material actually in the sample. So our opening photo, we have this, and I have here what inferences can be made about the density of the solution. And what solution? Now, this is a solution. This is liquid water out here. This is solid sugar. So when you're dissolving this, you make a solution, and you'll notice that solution is sinking. So that density of that solution should be higher. And sure enough, if you make a sugar solution, it will sink to the bottom of if you don't agitate it or stir it. So remember, density equals mass over volume. So you want to keep that in your mind, that that's a relationship of density. So if we were to use this relationship, a piece of platinum metal with a certain density has a volume. What is its mass? So you would use the D equals M over V relationship. Rearrange the formulas, and you would get M equals D times V. You're being asked for mass. And when you do calculations, always make sure to include units in all numbers. I'll kind of take points off for you if you don't, because I get really lost in calculations sometimes if people don't include units. So you'll notice here, then the centimeters cubed cancels out and you're left in grams. So that's how much mass would be in that size sample platinum. And there's the cancellation of the units again. So your book gives you a little table here of densities, and those densities are of some common samples of things like air, ethanol, water, and they got osmium, and it's the most densest element known, which is kind of neat. It's even more dense than gold. It's probably worth more money too, purified anyway. So that's just to give you an idea of the density of some common materials. So as far as temperature is concerned, the temperature scales that we will be dealing with are Kelvin, Celsius, not Fahrenheit, but of course we still deal in Fahrenheit in the United States, so we need to know the difference and how to interconvert them. Those formulas are given on that sheet that I wanted you to print out, but we basically use Kelvin and Celsius for lab work. And what I do want you to notice here, because this is important later when we do thermochemistry, is that the units between Kelvin and Celsius are the same size. So if you were to look at the ticks on the thermometer that measured in Kelvin, even though there's no such thing, and the ticks that are in Celsius, they're the same size. So if you had a change in temperature, say of 5, it would be the same, 5 degrees Kelvin, 5 degrees Celsius. It wouldn't make any difference, but not for Fahrenheit. Fahrenheit would be a different delta T because the ticks are not the same size. So to interconvert between those, remember that Kelvin is equal to your degrees Celsius plus 273. This 273 is 0 Kelvin is negative 273 degrees Celsius. So that's why you have to add 273 to your Celsius all the time. So 0 degrees Celsius is 273. And there it is. 0 degrees Celsius is 273 Kelvin. And then 100 degrees. So this is the freezing point of water, and this is the boiling point of water. Now remember, water is the most common substance on the planet, and that's why a lot of things are based on water. So water is the standard. Here's a formula for Fahrenheit to Celsius. And there's your markers for Fahrenheit is 32 degrees is freezing, 212 is boiling. Now let's talk about scientific notation. Scientific notation is a way to write numbers that are really, really big or really, really small. And they're written in such a way that, let me get down to here on this slide. This is a really big number. That's Avogadro's number. This is a really small number, mass of a single carbon atom in grams. And to write scientific notation, you have a certain part here. This is the number portion, and then you multiply that number by 10 so many times or divide by 10 so many times. Here you would be multiplying this number by 10 so many times to get the true number. Here you would be dividing by 10 so many times to get to this number. So when you write scientific notation, that portion of scientific notation is a number between 1 and 10, or 9.999. And that is a positive or a negative integer, as I indicated up here. So scientific notation, if we put these numbers into scientific notation, this 568.762 becomes 5.68762 times 10 to the second. So all of these numbers are significant, so they should come down into the scientific notation number portion. Now, if you have one that's smaller, you move the decimal to the right. And again, this guy has 3 significant figures, and that's why they all come to this spot. Now I moved it how many times to the right? 1, 2, 3, 4, 5, 6, and that's where the -6 comes from right here. So this number, 7.72 times 10 to the -6, has 3 significant figures. So keep on going with significant figures. Now you've probably been beat to death with this over your career of education, because significant figures are important in the fact that when you use measuring devices, the number of significant figures that comes from a measuring device tells you how precise and therefore not how accurate, but it can be more accurate than other measuring devices that don't have as many significant figures. So the number of significant figures in a measurement, of course, when you look at a number that is a measurement, any digit that is not 0 is significant. For example, all of these are significant, and that means if this is a mass, this balance here, however you balance, whatever balance you used, is reading to this is kilograms, so what would this be? This would be 1, 2, 3, 4 grams. But notice it's not 0.0. It's reading to the ones place is what this is reading to. So this is not a very good balance, but it's for very large, so maybe that's why. But either way, it's reading to the ones place, but it still has 4 significant figures because they're all non-zero. Zeros between non-zero digits are significant. For example, this has 3 significant figures. This is part of the measurement. Zeros to the left of the first non-zero digit are not significant. This only has 1 significant figure. These are not significant. So if you were to write this in scientific notation, it would be 8 times 10 to the -2 liters. And there's your 1 significant figure. If a number is greater than 1, then all zeros to the right of the decimal point are significant. For example, 2.0 is 2 significant figures. It's in milligrams. So it was saying the balance we used was able to measure to the 10th of a milligram. If it's less than 1, then only the zeros that are at the end and in the middle of the number are significant. For example, these are not significant. This one is. So if you write this in scientific notation, you would see it to be 4.20 times 10 to the -3rd grams. So there's your 3 significant figures. So let's look at practice here. How many significant figures are in each of the following? Since they're both non-zero, 2. For this one, since the zeros are trapped in between 2 non-zero digits, 4. This one is a decimal, has zeros out front and a 0 behind. These are not significant, but that one is 3. This one is already in scientific notation, so all you got to do is look at this portion and that count the number of digits there, and it is 2 for this one. This one is a whole number. Now, this 0 is not significant in this situation. Now, we'll see a couple different things here, and you say, apparently the balance that I used to measure this mass was only read to the tens. Now, that means that this number has 2 significant figures. But what if my balance, like on the previous slide, read to the ones? Now, I can't put 0.0 because that means to the tenths, but I can put a point here. Now, this would have 3 significant figures. And that point there means it's reading to the ones place. Now, what do we do with significant figures when we add and subtract? We have to carry the correct number of significant figures through our calculations. How to do that with addition and subtraction? When you're adding and subtracting decimal numbers, you have to look at each of the individual numbers, and then when you add and subtract the numbers, you round your final answer to reflect the least precise answer. Now, we got to be careful with the words precision and accuracy. We're going to talk about that a little bit more here in a second, but the more precise the number is, the more decimals it has, the more significant figures it has. Now, when we're doing decimals, these two situations here, this has 3 after the decimal and only 1 after the decimal. But when we add and subtract numbers, we have to round the answer to the number with the least number of significant figures. Now, when we're doing decimals, we only looked after the decimal. So we have to round this number to 1 significant figure after the decimal, because we couldn't round it to only 2 significant figures. I mean, we could, but that would give you 90, and then 90 has only 2 significant figures, and that you lose a lot of information in there that you didn't need to lose, because this did read to the tens place, so we want to keep that like we did over here. For an example of subtraction, again, looks like this guy has 2 after the decimal, so that's the less precise of the 2, so you round to 2 after the decimal. For multiplication or division, you look at the two numbers and see which one has the least number of significant figures, and then you round it to reflect that one. So this one has 3 significant figures, this one has 5, so you would round this one to only 3 significant figures. This one has 2 significant figures, this one has, so we round it to 2. This one has 5 significant figures. We would round this one to 2 significant figures, which would be 0.061. For exact numbers are numbers from definitions or counted. So an exact number, for example, if I was to do a calculation like this, if I want to take the average of 3 numbers, I divide it by 3. But you can't take the number of significant figures of this one. It doesn't have significant figures. It's just dividing it by 3. It's not one of the measured numbers. So we would still add them together first and divide by 3, but we would still need to use the number of significant figures that was reflective of the measurements. So let's talk about accuracy and precision. You've probably seen this picture 1,000 times. They're always talking about this one is accurate and precise. This one is precise but not accurate, and this is neither accurate nor precise. But what does that really mean? I mean, accuracy is as close as you can get to the true value. Precision of a set of measurements is how close they are to each other, even if they are not accurate. So if you don't know what the true value is, you can never make decisions about accuracy. Precision, on the other hand, you can make decisions about, and the more precise an instrument is, for example, the more precision a set of their measurements would reflect. Now, I know that sounded kind of weird, but let me give you an example. If you have a measurement of 1.135, now I can say that's a pretty precise measurement. It's precise in the fact that if I were to take many measurements, I might get something like 1.137, 1.138, or whatever. These are all pretty close to each other. And notice all the first 3 digits are the same. So when you have instruments that go out to many decimals like this, that means that they are pretty darn precise, and their set of measurements will be closer to each other. Now you would compare that. If, say, I had a balance, this balance measured to the thousandths place. There's a balance in the lab that only measures to the hundredths, and then you can have balances that only measure to the tenths. So say I had a balance that measured to the tenths, and I got 1.1 one time and 1.3 the next and 1.4 the next. These are actually much further apart from each other and therefore less precise than this set is over here. So precision for a set of measurements, you can say, well, these are precise. Well, compared to what? I mean, if these are more precise, even though they're kind of the same. So precision for a set of measurements is how close they are to each other. A precise number usually means a number with more decimals because it was made with an instrument that had a higher precision. Accuracy, you really have no idea. Accuracy, you have to know when your instrument was last calibrated and what it was calibrated with. So accuracy is how close it is to the true value, but precision is kind of thrown around, so we just have to be aware of what that means. And I drew over that there, but accuracy is how close they are to a true value, and precision is how close they are to each other. Now let's talk about dimensional analysis. I know this lecture is getting a little bit long here, but with dimensional analysis is a way to dig yourself out of any hole of calculations using units. Now I know that sounds weird, but it kind of makes life a little bit easier when you are doing calculations for chemistry or for physics or for mathematics. You want to have units. The units give you information about the numbers, and then also give you information about how you could manipulate those numbers to get a different value in a different unit. And a lot of times that's how people discovered things, especially physicists. They discovered the mass of the electron, the charge on an electron, things like that. That was not by direct measurement, it was by inference and by dimensional analysis and mathematics. So anyway, Let's look at what dimensional analysis is. How would you do this type of problem? You say, how many milliliters are in 1.63 liters? Now, if you know that there's 1,000 milliliters in a liter, you might know just to move this over 3 spaces, and then you'd have 1630 milliliters. Now, I want you to notice 3 sig figs, 3 sig figs. I didn't change that. But how would you do this? As far as dimensional analysis is concerned, dimensional analysis is a way to set up calculations in which you can cancel out units. So if you look at this, you can see that these would cancel out. You are, in essence, changing the unit from liters to milliliters. Now, I want you to notice this is not correct, because how can you sometimes you say, should I divide by 1,000? Should I multiply by 1,000? Well, it depends. It depends on what your units tell you. Your units should line up in the fact that they should cancel each other like they did up here. These canceled each other and left you in milliliters. These are not canceling. If you did a calculation like this, your final unit is liter times liter is liter squared, and then you would have liters squared per milliliter, and that would be incorrect. So you just got to be careful, and if you make sure your units cancel properly, a lot of times you don't even need to know the relationship. If you say you forgot that D equals M over V, you could still wing it if you knew what the units are and all the numbers and what unit you wanted to get to. So an example of that would be something like this, where the speed of sound in air is about 343 meters per second. What is the speed in miles per hour? Now, this is a conversion problem, and a conversion problem is converting meters to miles and seconds to hours. And almost all problems like that are kind of like conversion problems. You're converting one thing to another. So you see, you start with your number here, 343 meters per second. And what is this step doing? And this is taking meters to miles. And our second step is taking minutes, seconds to minutes. But notice you wanted minutes on the bottom, and that's why you have this set up this way, seconds and seconds. And then I'm taking minutes to hours on the bottom. And then if you do your cancellation across the way here, your meters cancel properly, seconds cancel properly, minutes cancel properly, and you're left